I have a bunch of different interests, and one of them is doing tools for data science. The other is history and philosophy of programming. And when I was thinking what talk to do here, I sort of decided that maybe this is the safer one, because different bits of history are not allowed in Poland. So I didn't want to get into history of type that's banned and put me in prison. So instead, I'm going to be talking about live coding. And this is a piece of work that I've been doing in the Alan Turing Institute, which is a sort of UK institute that does data science. And there's sort of lots of people around who do very fancy machine learning, but a couple of people who are sort of interested in improving the tools that people use when working with data. And the context for this is it got a lot easier to explain my research interests thanks to these people, because there's this sort of name for it called post-fact or sort of fake news, where, for example, in the UK, people sort of don't really find facts and truth all that interesting. Which, if you're interested in data science, is kind of sad, because all your work is about sort of how can we make the data more accessible. So how can we make sort of data more accessible so that people care about them and are actually sort of interested in finding what the data can tell us. And there's this sort of recent trend that some newspapers have been looking at. So this is an example from the New York Times, where they're sort of visualizing data in some really sort of accessible ways to encourage people to sort of see what the data says. So this example is when they were looking at the history of Olympic Games, and they sort of draw the history of medals. So there's sort of, over time, you can see which countries get more medals, which get fewer medals. And I find this really nice, because with just sort of this one picture that is based on some actual facts, on some actual data set, it tells quite a lot of things. So right here, you can see 2 Olympic Games didn't happen because that's the 2 world wars. There's this peak around here, where in 1980s, first the US didn't go to the Olympics in the Soviet Union, and then sort of next year or next 4 years it reversed. So you can see the Cold War in this, and I think it's a way of sort of engaging, making data more engaging, getting people interested. But even this, so this has a couple of problems. One is that pretty much the only people who can do it are New York Times, because they have so many developers who know everything from R to JavaScript, D3. They wrote D3, so that helps. It's really hard. And so what I'm sort of interested in is, can we make this easier so that if you're a not necessarily sort of random person off the street, but at least sort of university-educated person, you should be able to somehow look at the code, try to sort of understand how it's been done, check that you could recreate it, check that the visualization isn't misleading, and be able to explore further. So with the Olympics, for example, if you count football or ice hockey winning, you can count it as 1 medal for the team, or you can count it as like 15 medals for every single player. That really skews the data. So what I've been working on is this project called the Gamma, and I'll give you links to everything later on, where the idea is, and this just runs everything in the browser, the idea is whenever you see a chart, you should be able to see how it's been created. So this is an example where I'm looking at carbon emissions and comparing carbon emissions of China and the US. And you can see that China is winning pretty clearly. And this is looking at but that's sort of, what does it really tell me? Well, I can look at the source code here, and this has a little scripting language, which I'll be talking about more later on, where you can access some data. And for example, what I'm doing here is that I'm saying, looking at some data from the World Bank, give me the carbon emissions in kilotons. Now, this is one of the several things you can look at, and carbon emissions in kilotons is the sort of total number for the country. And if you compare this for China and the US, well, there's obviously a lot more people living in China. So maybe that's misleading, and maybe what we want to know instead is metric tons per capita, which is basically sort of how much is it for one person living there. So if I change it here and here, well then if I didn't resize my window, then there would be a nice update button here, and I could change it. So instead of changing it through the code, I can also change it here, because I can analyze the code and find bits where there's some variability. And so I can do the change here. And this is something that you can do even if you're not a programmer, but behind the scenes, it's actually analyzing and modifying the code. And so now, if you look at carbon emissions per capita, you can see that US is actually much worse polluter relatively per person than, say, China. So that's the kind of transparency that I think is really, really important when we make data available. And the whole project evolved into how can we make this easier, because currently you can build this sort of data visualization. You probably need PhD in computer science and PhD in data science to just be able to do this. So how can we sort of make it easy for a regular journalist who's maybe technically skilled but not sort of expert to produce these kinds of visualizations? And there's a nice talk by Jonathan Edwards, which is in a different context, but he talks about this gap between spreadsheets on one side and programming on the other, where spreadsheets, you can use them to solve fairly simple problems, but lots of people can do it. Programming, there's sort of, even the simplest programming problem is fairly hard, but you can solve arbitrary complicated things, but only a little number of people can actually do this. And I'm basically interested in what's somewhere in the middle. Like, can we make something that's easier than programming, but more powerful than spreadsheets? And one idea that's really great about spreadsheets is that when you're doing something, you're working with your data live. You're not writing some abstract variables, f and free monad 1. You're working with actual numbers. So in Excel, if you want to add two things or multiply, you just sort of look and work with the data directly, and then you extend your computation. And so the main thing I want to sort of talk about is behind the scenes of this part of the project where, and I'll do refresh to make sure my window size is right. All right. So what this is doing is that as I'm typing, it will give me live preview of sort of the code, what's the result of the code that I wrote so far. That's one thing. The other thing is that this is sort of inspired by F# type providers, even though it's not, this is not actually F#, the code here. It's my own language that runs in the browser. And I can say things like, so let's look at who's won the largest number of Olympic medals in Rio. Games is Rio, and all I'm doing is sort of typing dot and choosing one of the options here. So the talk is an advertisement for autocomplete. And if I say, give me RIA, then I can do some grouping. And here I'm doing this sort of by writing code, and the preview updates live. This is even a bit more fancy because I can say, I can click on things and it will write the code for me. So if I want to know the number of gold medals per person, then I can do paging. What do I want? No, I want to sort it first. So it tries to be a bit more like spreadsheets rather than being like a proper programming language. But actually, there's still code behind everything you're doing. So this is how you can get the number of gold medals. And I'm going to cheat, and with a bit more effort, it's not significantly longer. I can put it on a chart that you could embed in an article. But really, the sort of interesting thing technically is that as you're going through this code here, this doesn't quite fit, but as you're going through this code, it gives you preview for where exactly you are in the code. And if I change something, it pretty quickly reacts and comes back with the updated page, updated result. So that's the interesting problem. How do you actually implement sort of editor or a programming language where, as you're typing, you get live previews and sort of changes are evaluated reasonably efficiently? So if you start thinking, I'll write my own language, and you read a textbook on writing programming languages, then the textbook compiler has a couple of properties. The usual textbook compiler is batch-based, so the idea is you give it a file, it will work, you go get some coffee because it's compiling, you come back, and you have a result. And the way it works is that it sort of builds and transforms trees, so it parses the code, then walks over the structure a couple of times, and then it produces a binary. And a textbook compiler can also read bad programs. So if you make forget a closing bracket, it can tell you, haha, I can't do anything, fix your brackets. And that's things that you can't really do in live coding. But let's start by looking at textbook compilers. And so the example that I'll be using for the talk is not going to be the fancy data science thing because that's too complicated. But I've built a very simple version of it where you can do some image manipulations. And so as a toy example, we'll try to build a live programming environment where you can write code like this, and it will blur images and compose them, and we should be able to sort of modify the code on the fly. So if you're in a sort of standard compiler mode, then when you see something like this, you build a tree from this where the first thing I have is that overall this is a lead binding where I'm defining a variable p, and what I'm assigning to it is a call to this load method. All right. And load takes 2 arguments. One of them is image, that's the instance, and the other is Pope PNG, which is a string. Then what does it do in the body? It calls blur, and blur takes p, and then it takes 5 as another argument. So normal compiler will build this tree, and that's the result of parsing, and then it will walk over the tree a number of times. So if you like typed programming languages, the first thing it will do is that it will assign type. So this is some class. Pope is a string. And then the result of load is an image. And then when we look at the body, P, we know that's the result of load. So this is an image as well. This is an int. And then if I call blur, I get back another image. And the overall result of this is, again, an image. So normal compiler will build this tree, and then it will walk over it to do the type checking. In the next phase, it will walk over it again and do the evaluation if you're writing an interpreter. So image will be some object. This is still a string. Then it will load the image. The result of this will be a picture of a pope. Then pope goes back here. That's still pope. This is 5. And then we're going to blur pope. So this is a blurry pope. And then blurry pope as my overall result here. Yeah. So that's how normal compiler works. And we'll start by doing this. But we'll see that this is really tricky because every time you change your program, you have to rebuild the tree and rerun everything. But it's a good starting point if we want to understand what we're doing. So I have right here a little live coding environment for demo where I can do things like 1 plus 2, and I see 3. Or 1 plus 5 is 6, and it prints some statistics that will be relevant later. And the programming language behind this is really super simple. So I have an expression, which can be basic things like numbers, strings, and binary operations. I can access members, so it's dot property. I can do dot or invoke with some arguments. I can have variables, and I do let bindings where you say let p. So let some variable equals this expression, and then the body following it is this expression. And so far, I've written an evaluator for some of those things. So basically an interpreter, where if I get a number, n, I'll just return that number as an object. If I get a string s, I'll get that as an object. If I get a variable, then I'll see I'm carrying around this context, which is a mapping of all the variables that I've defined already. So for every variable in scope, I have its value, and I'll try to find the variable. If I access some variable, then it says variable is not defined. So this is working. Binary will run the operation. And what I want to show you is 2 bits. So if I have a member accessed, then what I'm going to do is object node is this instance. That's the expression, the sort of instance on which I'm doing the member access. And I'm inside a function evaluate expression. So I'll just call myself recursively with the same variables. And this gives me the instance. And the way I'm running this is that I'm just interpreting this or running this as JavaScript. So what I'm going to do here is say get property, which is JavaScript. What did I just do? Get property, which is some JavaScript binding that will do a dynamic lookup in this object. And I'm going to access this name. So you're basically walking over the tree recursively, and at every node you do some basic thing. If I have a let binding, so this is more fun because now I'm defining a new variable. I'm going to evaluate the assignment. So if you say let p equals 1 plus 2, let's first evaluate 1 plus 2. Let's evaluate assign. And then the next step is I want to evaluate the body, but I want to keep this new variable. So I'm going to say evaluate expression. And this was red because I'm wrapping all these expressions in some node object, so I need to do .node. And here, I want to evaluate the body, but with a new set of variables where I'm going to add this new variable that I've just defined. So what is it that I'm doing? Var is a string. This is my key. And I'm going to assign the thing I evaluated as the value of the variable into my variables and evaluate the body. So basically, all the tree transformations, this is where functional languages are really nice because you're just walking over trees and evaluating things. I'm not going to implement call because this is a bit too long. But calling, again, you just say, evaluate the instance, evaluate all the arguments, and get the property and invoke the operation. So with all these changes, if I go here, 1 plus 2 still works, so that's nice. And I have 2 pictures here in my folder. So now I can call image.loadPope, and it will evaluate the expression, and we'll see a picture of Pope Francis. And now the numbers are important because it tells you how long took the parsing, so that's pretty quick. Binding is something I'll get to next. But then the evaluation here, it took like 600 milliseconds because it was actually loading the file. If I change it, well, now it's just still loading the file, so it takes some number of milliseconds, but it's not doing the request again. And then I have a couple of operations, like grayscale. Maybe not. What did I do? Huh, there's grayscale Pope. I'm not handling new lines properly. I guess that's the problem. So now I've got Pope with a grayscale. You can see it took 500 milliseconds. And if I do something like blur, blur is fun. You can see my cursor is stuck because blurring is slow. This took like 3 seconds. And now if I start typing, then you see it gets really painful because every time I type a key, it will have to reparse the code and walk over the whole tree again. So it still hasn't finished. No, no. So that's why we need something better than a textbook compiler, because the textbook compiler is working as a batch-based thing. So every time I do a change in the code, it will think, you have to do it again from scratch, and you throw away everything that you've done before. So how can we do this better? The idea here is that rather than, well, what do we actually need? So if we want to deal with an environment where you're modifying the code live as you go, then first of all, we will definitely somehow need to cache the results. And I just can't, if every time you change your code, I can't run it from scratch. So I need some sort of caching. And in this demo, I'm doing just an evaluator or an interpreter. But if you're writing a compiler, you need the same things. You need sort of to cache the results of type checker, cache the results of optimizers, and so on. And the way we can do this is that rather than walking over this tree, we'll build some dependency graph that will reuse things that we've seen before. And the other fun things about live compiler is that it needs to be able to accept bad programs. Because if I'm here, so the way I can make this reasonable I'm just curious where I messed up with my, there it is. Yeah, I'm not allowing spaces before dot, apparently. So here, if I change the code and break it by sort of doing maybe backslash. No, backslash is still allowed. So what other characters do I have? At, maybe. There it is. If I end up in a state where the parser fails, then I can happily edit my code because the parser will just fail and the compiler can't run it because it's not a valid program. But the problem is when you're writing code, most of the time, your code is not valid. Like if I open a parentheses, then I'm in the middle of writing, but if I'm in a batch mode, well then, yes, this is not a valid program, but if I'm live coding, then the environment should still be able to parse this and work on it, and maybe even give me a preview without the invalid bit. So that's the other tricky thing here. So we need something that will cache the results and accept bad programs and work in some more clever way. And the key idea here is that, where am I? So previously, what we've been doing is building all those trees, and now, so we've been building all those trees and then walking over the tree. But what we are going to do next is that we'll still start with a tree. We'll still run the parser to build the tree. And as you can see in the numbers here, the parsing is the fast part. That doesn't take very long. So parsing is fast. We'll build the tree. But then the key trick is that once we have the tree, we will turn it into some sort of dependency graph. So here, for example, I'll create a node for this image, and I'll create a node for my string. And those are just primitive things that I have already. And then for load, I'll create a new node that depends on these. So far, it looks pretty similar. But now, I'm going to break the structure a bit, and I'll remember this is a node for P right here, and then I go into the body and I'll create a node for blur, and this will directly depend on the P. And so we still have 5, that's a primitive value, and I depend on that as well, and then my main thing depends on this. So I've parsed the code, built a dependency graph, and then I'm going to do all the same things I've done before. So image is some sort of object. Pope is a string that I'll evaluate. Load will give me normal Pope. And then this is 5. The result of blurring is a blurry Pope. This is tricky. And one more blurry Pope goes here. Yeah. So this was the sort of, when you come to this first, but then what I'm going to do next is when you modify the code, as I'm building the tree, I will actually look at the previous tree I've built and reuse bits of it. So as I'm building the tree, I'll go to my image and I'll say, have I ever seen image before? And I will find out that I have, and I have this node which already has a value for image. Then I go next and I say, load this. Again, this is a node I've seen before, so it will already have a value. Then I go here, and I need a node for load that depends on these two nodes. And again, this is something I've seen before. I'll cache it in some way, and as I'm building the graph, I'll just pick the node that I've seen already, which already has a value. Then I'll go to blur, and now, so I've changed the code so that it does blur 7 rather than blur 5. And that's where now I don't have in my cache a node with the same dependencies. So now I'll be like, well, now I actually need to do something new. So rather than rather than reusing previous nodes, now I actually have to build a new node. And this one doesn't have a value yet, but it depends on this node from here, which already has a value. It depends on this, which doesn't have a value. And then the overall result is a new node. So you can see that when I change some bit of code, what I can do is that as I'm building this dependency graph, I'll take bits that I've seen before, and for those, I will keep the values I've evaluated before. And then when I need a preview for the new version of the code, I'll just have to evaluate the remaining bits. So I'll evaluate this to 7, and I have a pope already. But now I'll create very blurry pope because 7 is more than 5. And this is going to be my overall result. Oh, what happened? What do you see there? No, that's not my screen. Can I get my screen back? I'll try to plug it on and off. Is it not my fault? That would be surprising. I want my screen back. I was just, oh, did I touch something on here? Ah, this is clever. Yay! OK, I will not touch this. That's all right. No problem. There's a hidden control panel. I can launch the missiles if you're naughty. So this is now newly evaluated blurry, very blurry pope because I set this to 7. So I hope you didn't lose the screen too far back. But the key idea is that as I'm building this dependency graph, I can now reuse bits that I've evaluated before. And the way I'm going to do this is that I'll just build a cache of nodes where the key is going to be what kind of node is it, and what are some hashes of the dependencies. And then I'll just, every time I need to build a node in the graph, I'll say, have I seen this before? And if yes, I'll pick one that I've seen already. And if no, then I'll create new node, which is the purple here, and then those new nodes I'll have to evaluate later on. So to do this, here, this is my representation of the code as an expression, as a syntax tree. And I'm adding a new one, which will be the nodes in the dependency graph. And this is very, very similar to the previous one. You can see one change here is that there's no let binding, because let is really erased in the dependency graph. That's just sort of becomes a direct link. And then an entity has a node in the graph, has what kind of node it is, and also some sort of hash. And I'm being naughty functional programmer here, a mutable state with a value, which will start as not evaluated, it will be none. And then when I evaluate it the first time, I'll set this to some, and then I don't have to re-evaluate it again. And my evaluator for this is going to be very similar, actually even simpler than the one we've written before. So if I have a constant, well, then I just return the value. If it's an operator, then I'll evaluate the operator. But one important thing here, well, I'll get back to that in a second. Then if I have member access, member call, again, this is going to be pretty much the same things we've done before. So we evaluate recursively the instance. We get the property. Here we evaluate recursively the instance, the arguments, call the application. The one interesting thing is that if I have a sort of node that represents the variable binding, then I don't have to do anything sort of clever, because the clever thing has already been done when building the tree. So I just evaluate the body, and when I have a reference to a variable, I'll just evaluate the node that this represents. The one tricky thing that I didn't show you is in binder. So binder is another sort of, is the thing that walks over the tree and builds the graph. And what I'm doing here is that I'm defining all these entities. And you can have a look at the code, explore further on. But the clever bit is here inside bind entity, where I say, given this node that I'm creating, get me some code that represents the node, and all its antecedents, what it depends on, and then I collect their hashes, and I have this dictionary where I say, let's try to find a node in this dictionary with these children, with these parents, and if it's there, then just return the existing node, which might already have a value. And if it's new, well, then we'll create a new one with a new hash and remember it for later. So we've written the evaluator here, and the last bit is that this is my sort of entry point for the program. And I've got, this is written using Fable, using the Elm architecture. So here I have a rendering function that generates all the HTML. And here I have an update function that when you change the code, it will, there's lots of performance now so that I can check how long things take. I try to parse the code. Then I call the binder, which is the bit that walks over the tree and builds the dependency graph by reusing nodes. And then previously, I was just doing evaluate expression every time, a fresh, old style. Now we are going to change it to evaluate entity. And this will now work, rather than on the tree, it will work on the graph. So we've done the change here. And assuming everything worked, we'll see how that goes. Let me actually open debugging tools here so that you can see a bit what's going on. Let's make this bigger. So you can see that the binder, I'll refresh it again. There's a couple of log messages. So if I say 1, it says new binding for number 1. If I say +2, then it says cached binding number 1, new binding number 2. This means that, and new binding for the plus operator. This means that it reused some of the nodes when building the graph. If I put parentheses around it, then this just reused the cached nodes. So this change didn't modify the tree at all. If I say times 3, then it's still reusing the nodes for 1, 2, the plus operator, and it's creating some new nodes for 3 and the multiplication. So in this change, as it was evaluating it, it was actually just reusing 1 plus 2. Now, I was actually lying because there's one bit that I haven't finished in my code. As I was writing the evaluator, there's the function evaluate entity kind, which does the pattern matching, and it recursively calls evaluate entity. And evaluate entity is where we do the clever bit with storing the value. What I'm going to do here is if I want to get the value for an entity, I'll say, well, I'm going to do this in a naughty way, but if this value is not evaluated, then I'm going to evaluate the value and store it in my entity. And now this is definitely evaluated, so I'll just return the value. So this is where now I've done a change that as I'm walking over the graph, if I evaluate something, I'll actually store it there, and then it will get reused. So with adding numbers, you can't quite see that, but let's try with images. So if I say image load Pope, then it loads Pope. That's all right. What I'm going to do. So if I have pope, and then I do pope.blur 5. This is the bit that takes long. It's still blurring. It took 3 seconds to blur, but if I continue and I add grayscale, then the change took only 600 milliseconds because it was able to reuse the node I built previously for the blur operation, which had a value. So all I had to do here was to do one more operation and do the grayscaling. So I've got, and I did another change, and this was super fast because all the nodes that are here are already available. I have one more picture, shadow. Now the variable is not used anywhere, and that's why this was fast as well, because I'm not using it. If I change it, now this was slow because I'm blurring and grayscaling another image, and then I can do .combine, which takes another image and sort of a percentage of how much of which image you want to get. If we change this to 50 or 70, then it's producing a creepy image of a pope who is into F#, obviously, with a shading monster. So, and you can see that this is running sort of significantly faster than before, because if I change this number here, the update takes like half a second, because all it needs to do is to evaluate the last combine call. But the blurring and the grayscaling, that is something that I've done before, so it's cached, including the value. And if you did something more fancy, this would include the type checking and so on. All right, so that was the demo. What's the summary of this? Well, first of all, if you want to see this in a live sort of bigger thing, then have a look at thegamma.net or gamma.turing ACUK. I'll share the slides on Twitter so you can find it, which is the sort of project where I'm doing this for real on a simple data science environment for aggregating data. The other two things that I was using along the way is that all the code was written in F#, and I think the sort of pragmatic functional first nature of F# made this really easy for two reasons. First, I was able to just use mutation when it was useful. So most of the code was purely functional tree transformations, which is great. But some of the caching, that's just a hash table or storing a value. So the style works really nicely for that. The other thing I was using is the Fable compiler, which is F# to JavaScript. And you could sort of see that throughout the demo, where as I was typing the code, when I made the change and saved it, it was immediately refreshed in the browser. And this is great feature that Fable gets by being integrated with the Node.js ecosystem. So all I had here was this command line thing running in the background with the Fable daemon and Webpack, and that was making all these things possible. Now, if you're interested in building your own live coding environments, two hints are build dependency graphs and work over dependency graphs and use them to cache the evaluation results. And good luck writing a decent parser, because that's the tricky bit where as you're typing your code, you want a parser that will recover when there's like a missing parentheses, and you basically have to guess what the programmer intends to write in the next step. That's it. So now you know how to write your own live coding environment. Thank you.
So we have time for one question, and then I guess you can get Tomas after the talk.
You have a chance to ask one question, or does everybody just want to go for lunch? There's a question here.
All right, I see it.
If you want to chat later on, I'll be around until the end of the day. So,
could you maybe say a few words about how the cache invalidation is done? Since I imagine that if you delete a reference because you're live coding, maybe you don't want to wipe it immediately or something like that.
Yeah, so the question was how is the cache invalidation done? The way the cache works is that when I build a node, I never actually change it. So like in this example that I was trying to explain here with the picture, in the code, I changed the parameter from 5 to 7. But when I was building the graph, I just created a new node for 7, rather than modifying an existing one. So the nodes are immutable. And if the code changes, then I'll just have to generate new nodes. And in my cache, I'll have sort of nodes for the previous parameters. But as I'm building the tree, I'll just create new ones. So I never need to, like, once I evaluate a value, it never becomes invalid. It can become irrelevant because I've changed my code and this node is never going to be used again. And that's a bit I'm not really doing well in this demo. Like, normally what I was going to implement was after sort of some number of iterations where the node wasn't used, you can delete it from the cache. But that's just for memory reasons. I never need to remove nodes because they would change. So it's sort of building a nice, the graph itself is built as an immutable thing. Thanks.
Thank you.
All right, that's it. Time for lunch. Thanks very much.